My name is Soutick. I'm a bioinformatics developer at Wolfram Alpha, and today I'm going to talk about what's new in biomolecules in Wolfram Language. Thank you so much for taking the time to come to my talk. Yeah, and before I start, here is the QR code for the talk notebook, which is uploaded in the cloud. Most of the functionalities are already in version 14.3, so it should work. Some of them that will be in the upcoming version will not work. But yeah, I will mention which one of them are planned for the next version. And here is the link to the notebook, which I have also pasted in the chat. Yeah, so today I'm going to be mostly talking about proteins, but proteins are not the only molecules of life. So biomolecules consist of proteins, which are composed of amino acids. We also have RNA and DNA, which are composed of nucleic acids. We also have carbohydrates and lipids, which are pretty important to biological functions. So proteins are linear chains of amino acids that is in general folded into pretty specific shapes, which is determined by the sequences or the amino acid sequences. And it's like, it has a hierarchical structure. So this is kind of like the hierarchy. So you have primary structure, which is basically just the string of amino acids covalently connected to one another by a peptide bond. These, using hydrogen bonds, can form secondary structures like helices and sheets. The helices and sheets, using electrostatic and van der Waals forces, can come together to form tertiary structure like this. And a tertiary structure is like a continuous chain of amino acids, and multiple chains can also then come together to form a protein complex, or which is also known as a quaternary structure like this. And this is like obviously cartoon representation of what actually proteins look like. So shapes for most part determine the functions of the protein, and proteins have myriad of functions in our body. It is essential to life. It supports biochemical catalysis, hormones. It can function as enzymes and also initiators of cellular death, which is also like important to our health. So what are amino acids? So these are the building blocks of proteins. They have this general structure like this. It has all amino acids have an alpha carbon, a hydrogen atom, a carboxyl group, and an amino group. It has another organic group or R group, which varies between amino acids, and all the variation we see in nature when it comes to amino acids, which gives rise to different shapes in proteins, is because of this variation in R group. So these are the 20 most commonly found amino acids, 20 most commonly found amino acids in nature that forms natural proteins. These are their structures. And as you can see, this is the carboxyl group and amino group, and the R group varies between structures. So there is a really nice function that came in version 14.3. It's called molecular feature distance, which helps you compute the distance, or like it's a metric that helps you calculate what is kind of the difference between two molecules. So, and you can use this to form a clustering tree to show actually how the protein structures are organized. And this can be also a really nice tool to teach students like how they are different. So here at the top, you have protein, which is in its only because it has very unique functions when it comes to protein structure formation, particularly like breaking of secondary structure or forming of loops. And then you can see here in this corner, you have another kind of group where it comes to like amino acids that have like rings, and then you have this linear kind of chains, which is like R group. So yeah, this is like a really nice way to visualize how amino acids are grouped together in the form of structures using molecule feature distance. Yeah, and then we come to nucleic acids, which forms DNA and RNA, which are very important molecules of life. And I'm not showing the entire nucleic acid because it has sugar and phosphate group. I'm just showing the base that defines what nucleic acids are. So you have adenine, thymine, guanine, in cytosine, the ATGC in DNA, and then you have uracil, which replaces thymine in RNA, right? So these are the structure of the bases. So let's look into carbohydrates, which is another molecule of life. Carbohydrates typically are composed of carbon, hydrogen, and oxygen. For simple sugars, it typically come in 1:2:1 ratio. So it's like has a formula of CnH2ON, and they act as the main energy source for most of our cells. So let's visualize the structure of three simple sugars, glucose, fructose, and galactose, with the same chemical formula but different arrangements of atoms. So here you can use chemical formula to get the chemical formula. So molecules, it has the same chemical formula, but I'm highlighting here the carboxyl group and OH group here. And as you can see, the arrangement of the carbonyl group is different in each of these three sugars and gives rise to different properties. And then let's look at a common lipid. It's very familiar to us. It's cholesterol, and this is the structure of the lipid, right? So moving on. So let's move into biomolecules, which is like the main focus of our talk today. So you can use biomolecule to get the structure of different proteins. So here we will visualize and analyze the structure of human hyaluronidase 1. I hope I'm pronouncing it correctly. It's an enzyme that breaks the carbohydrate hyaluronan in our body and is also involved in tumor suppression. So this is the biomolecular structure. So let's see the biomolecular structure of the protein. Right? So you can get the biomolecule using its PDB ID code. So this is like RCSB protein data bank, or PDB is a database that houses a lot of experimental structures, protein structures. So, and each of the structure has a unique 4-letter code. So we can get the structure using the unique code. This is the biomolecule object. It's as you can see, it's like a protein. It has 12 chains and other information that's useful. You can visualize the biomolecule using biomolecules.3D. So this is how the protein looks. It actually has one peptide chain, and the other chains are actually correspond to different ligands, as you can see here. You can use plot theme and color to see specific features or highlight specific features better. So I've used a different plot theme and set the color of the protein differently so that you can visualize the ligand and where it bounds a little bit better. So you have all this customization tools in the form of options that helps you like visualize a molecule as you want it to. So biomolecule has a lot of properties. The two really new and useful properties that came in 14.3 are Ramachandran angles and residue distance matrix, using which you can see the Ramachandran plot, which is like plots for torsion angles in the protein, and residue distance matrix will help you see protein contact map. So what do I mean by them? So if you use Ramachandran angles for the biomolecule, you can get like a quantity array. So for each of the residue, you have 2 angles, torsion angles phi and psi, and you can see it, how is it distributed, and each of the angles like to -180 and 180 degrees, and you can see how the angles are spread or distributed, right? And because this molecule has a lot of helices, this is kind of a typical feature of the Ramachandran plot. Many of the angles lie in this region, and if residues belong to helices, their corresponding phi psi pair will lie in the third quadrant, as you can see here. You can get the residue distance matrix, which is basically the matrix of the pairwise distance between residues in the biomolecule, and you can use a matrix plot to see like the protein contact map, which is kind of like a geometric signature of the protein. The unit of this is in angstroms, so you can see like the maximum length between two residues is around 77 angstroms, which is kind of like the rough size of the protein. And these are just the two properties. So if you just use properties, you can see how many properties right now are there in biomolecule. There is quite a few, right? Yep. Yeah. So let's move on. So another really cool feature that came in version 14.3 is the capability to structurally align two biomolecular structures. This is not restricted to protein. You can do RNA, DNA, or proteins, and using biomolecule align, right? So we kind of know, like we know that similar sequences leads to similar structures. So let us compare this property of protease by comparing myoglobin from two different organisms. So here we are comparing whale myoglobin and horse heart myoglobin with this PDB code. And as you can see, they do look pretty similar, but to quantify it further and do a proper comparison, we want to align this molecule, these two biomolecules with one another, structure it and then, right? So you can do that using biomolecular align. And what you get here, what you get here is basically the horse myoglobin will align itself to whale myoglobin and give the output, which is in this case an association. If you don't have these two on the right, then you would just get the biomolecule. So if you want the whole information, you get an association, and these are the different properties that you get as a return from this alignment, right? So these are really useful to actually quantify and see how good the alignment is, which I will show you in a minute. So the first thing we want to visualize it to see how good the alignment are. So here you can just use biomolecule plot to see the alignment, and in pink we have whale myoglobin, and in red we have horse heart myoglobin. As I said, they're almost like really, really good alignment. You can even see the two heme protein, not heme protein, heme molecule is also almost exactly aligned, which is really great. So let's see the difference between sequences, right? So that's something you can do from the biomolecule itself using the biosequences property. And you can see like there are some changes. So these are kind of substitutions. This is a deletion. This is a insertion. And there is a little bit of difference, but not too much, which again, like shows that like similar sequences can have really similar structure. And then there are all this information that's offered by the biomolecular line output. So you have how many residues are aligned, what's the error, which of the residues are actually aligned properly, what is the TM score. So TM score and RMS error are a really important metric to measure like how good the alignment is. So as you can see, if you do sequence character alignment, you can see most of the residues are really well aligned. As you can see here in green. You can get this metric TM score and RMS error. So TM score of anything I think above 8 or 8.5 is really great. The maximum is 1 for perfect alignment. So this is a really good alignment, which is also shown by RMS error. Anything I think under 1.5 angstrom shows excellent alignment. So this is like really great, which is expected, right? You can also do comparison of predicted structure versus experimental one. So right now we have the capacity to predict biomolecular structures using ESM fold. So here what we do is we get the biosequencers, amino acid sequence of the whale myoglobin, and basically predict the structure by just calling biomolecule on that. And then we do the alignment and we try to see the structure. This is the experimental and this is the predictor. Here you can see they also have really good alignment. So this is really great as a good comparison tool to see how good like AI models are when it comes to predicting protein structures. Right now, you can also, this was also introduced in 14.3. You can also fold proteins locally using using the option biomolecule folding method in biomolecule. So that's also gives you more control over like if you want to do things locally again and again. That's really useful. So let's move on. So I would talk about service connections. So this is a way in the language to access external databases. So we now have connections to different kind of bioinformatics databases. So there are 3 service connections that gives you access to over 1 billion protein structures. Users now have access to all the experimental structures in RCSD protein data bank, which is one of the best sources for experimental structures. You also have access to almost 772 million predicted structures in the ESM metagenomic atlas, and this is also one of the best sources for predicted structures of the metagenome. And metagenome are all the genome that's found kind of in obscure places of in the earth, like bottom of the ocean, or say like geysers and so on, right? So it's not like something that biologists deal with on a day-to-day basis in the lab, but it's still important. And then this is new in 14.3. Now you have access to over 240 million structures in the AlphaFold protein structure database, which is the best source for predicted structures of all organisms that are most relevant to biology. So this makes Wolfram right now one of the more comprehensive language that has access to so many different kind of structures. So you can create a new connection to the AlphaFold database using Service Connect. So let's see one such structure and analyze them and see what we can get from the service connection. So I'm looking at cellular tumor antigen P53, which is coming from the TP53 gene. And this is a really important protein because any kind of different mutations in this protein can lead to different kind of cancers, because this has a key role in tumor suppression, the protein in its like normal form. So here you can use the request biomolecule and its unique Unicode identifier. So any structure in the AlphaFold database is uses the Unicode ID. So using the Unicode ID, you can get the biomolecular structures, and this is a predicted structure using AlphaFold 2. And then you can visualize the protein using biomolecular plot. This is how the protein looks. And if you want more details about the structure, you can use the predicted structure details request with the same Unicode ID. So you can see like the name, the G, the biosequence, the organism, and so on, right? There's a lot of information here. And this is also kind of important, like many of the structures and many of the sequences in Unicode is not like reviewed by humans. So if the proteome and is a reference proteome, that means like widely used by biologists, and it's reviewed, that means like it has gone through an extra layer of review. So yeah, so this information is also provided here, which can be useful. So now we want to see like how good the structure is, because it's a structure predicted by an AI model, AlphaFold 2. So you can get two different metrics. So one is the predicted aligned error of the structures. So here it gives you a matrix of like the dimension of residue number times residue number in the unique angstroms. And predicted aligned error basically says like how well this residue X, residue I is aligned with another residue J, right? So if the value is really low, that means like the alignment is really good. If the value is really high, like here, then the alignment is not that good or not that confident in the relative positions of the residue, right? So you can see like in this protein, there's a big blob here, but for the other relative position on the residue, the model is not that confident. So another metric that you can use to see how confident the model is locally is predicted local, so PLDT of the protein. So that gives per residue value for the confidence. So the maximum value can be 100, minimum can be 0. And here you can see, this is interesting, that even the PLDT reflects that, like at the kind of like the center between 100 and 300, you have a really confidence chunk of the protein. So it's like robust. So the relative position we can expect should be good, and the others are not that confident. So here also we can see between 100 and 300, you have a robust chunk, and then you have a tiny kind of sliver of less confidence here, which you can see most likely is here, right? So these are the two ways you can actually numerically get how confident the like model is in the prediction, which is really useful. You can also get the predicted pathogenicity data for human proteins predicted by Alpha Missions, which is an AI model developed by Google DeepMind. So at this point, what it does is it only gives the predicted pathogenicity score for point mutations or substitutions in the protein. And it classifies them into either likely pathogenic or likely benign or ambiguous. So this kind of is an indication of like how likely that mutation is to cause disease. And this is like, mind you, this is the AI model, so more verification needs to be done, but this is like a really useful data. So you can use the request alpha misses pathogenicity and the immunoprot ID to get that data only for human proteins. And here you can see like for residue 1, it's methionine N goes to all the different other amino acids, and it gives a score between 0 and 1. So 1 is really likely. So anything that is very close to 1 is likely pathogenic. Anything that really close to 0 is likely benign, and anything in between is ambiguous. So this can also be really useful in doing some large scale analysis of in terms of like which mutations are likely to cause disease and so on. But this is like protein by protein, right? We do have a full alpha mission data in Wolfram data repository, which you can use to do large scale analysis, and you don't have to call like every single of the 20,000 or so proteins that exist in Arthropod database for humans. So that's something you can do using this alpha missions data in the data repository. So the new thing that got included is isoform data. So what isoform is proteins, a gene has exons and introns. So what happens when like translating into a protein is the introns get spliced out, and then the exons are joined by splicing, but you can have alternative splicing that gives rise to different ordering of the exons, which gives rise to different protein products. So from the same gene, you can get different proteins. So that's how I think humans have 90,000 different proteins in the body, but they have only 20,000 genes. So that's how you can get different more proteins than the number of protein coding genes that's there in the body. So like the TP53 has actually 8 isoforms, and this is the canonical structure, but then you have 2 through 9. So 8 out of isoforms, you can get the biomolecular structure for all the isoforms using the biomolecular request, and you can visualize them and so on, right? And they have pretty different structures, even though it might not seem so. They have different structure, and they also have pretty different sequences, as you can see here. So you can also get information about sequence from UniProt. It has around 200 million protein sequence data, and you can use the service connection UniProt and protein details to get actually information about the specific sequence. It has a lot of useful information that can be used for analysis. And you can also give a general text query. Here I'm searching for receptor tyrosine kinase and get the relevant hits from UniProt database. And you can do further analysis on like what do these individual entries mean. So this is another service connection that is upcoming in 15.0, and this is really useful. So this will give users access to protein domain data. So a protein domain is a region in a protein that is self-stabilizing and that folds independently from the rest of the protein. Each of the domain contains pretty compact 3-dimensional structure and most likely has pretty important biological function. So this is like a image of pyruvate kinase and different domains in it that can have different biological functions. The two service connections that we will have in 15 that will provide users access to domain data is CAP database and encyclopedia of domains. So CAP database gives users access to 151 million protein domains, which are classified into around 6,600 superfamilies from the experimental protein structures in the protein data bank. And encyclopedia of domains, which is a fairly recent database, will give access to 365 million structural domains in 214 million predicted structures in the AlphaFold database, right? So let's first look at the CAM database, which deals with experimental structures. When create a service connection, we are looking at glutamine synthesis. In terminal domain here, you can get the biomolecule or the structure of the domain giving this unique identifier with the domain ID. And you get the biomolecular structure. You can visualize obviously using biomolecular 3D. This is how it looks. You can get more details about the specific domain giving the domain ID and using the domain summary request. As you can see here, it has a lot of information. And using this part of this information, you can actually highlight the domain in the full protein structure. So here is the full protein structure of glutamine synthetase. And here is the specific domain that has been highlighted. So this can be really useful to see where domains lie in a protein, and that can be useful for biological analysis. So the domains are grouped into protein superfamilies based on similar structures and functions. There is a total of around 6,600 superfamilies in the CAT database. You can get the details of all the superfamilies. The top level detail using the superfamilies request like this. And you say it has unique identifiers, and then you have the names and so on. You can get a list of all protein domains belonging to a specific superfamily. As I said, super domains are grouped in superfamilies, so you can do the other way around. So you can use superfamily domains request and give a specific superfamily ID to get all the domains corresponding to this superfamily ID. And this is actually kept solid ID. So this is like further classification of this cat superfamily domain based on sequence similarity. I mean, each of the domain will have a unique cat ID, cat solid ID actually. This should have been cat solid ID. Okay. You can search for domains. This is also really powerful. You can search for domain, similar domains, just giving a biosequence or amino acid sequence. So here I'm looking for a sequence from the ASM atlas from a structure there, which is found in the metagenome, and I'm trying to look for structures in other databases using this domain search request. So I give this biosequence as the input, and it's going so fast. And here you can get all the outputs from the search with specific cat ID and other details, which can also be really useful for analysis. If you have a custom sequence that you want to search for, an encyclopedia of domains will give you access to like details about what domains lie in a specific structure in the AlphaFold database using the domains request and the unique UniProt ID. And you can also get the biomolecule using the biomolecule request for that domain. So here you get the like details about the domain, what domains lie in the specific structure. So here we would like to see where the domains lie in that specific structure, and we get the biomolecule from the AlphaFold database service connection here, and we can visualize the domains from the information of the domains request in this database. And this is where the domains lie in the predictor structure with this specific details. Yeah, with this, I've come to the end of my talk. I would like to dedicate this talk to Michael Trott. I think he was an incredible mentor and one of the kindest and smartest human beings I have met. I think it was really a great experience to come across someone like him, I think, who has touched so many people's lives in a really positive and meaningful way at Wolfram. And yeah, I was fortunate to know him during my short time at Wolfram, and he does continue to inspire me to be a better thinker and a kinder human being. Yeah, he was truly one of the best mentors I had. So yeah. And I would like to acknowledge that I'd like to thank Jason, my supervisor, and the Wolfram Alpha Chemistry and Biology team to helping me prepare for this talk and numerous feedbacks and code and so on. And for time for questions, and feel free to email me if you have any questions, ideas, or requests after his talks. I'll copy the email in the chat, and it's time for questions. So, Lord. Okay. So, let's see. There's a chat. In the chat, there's a question. Okay, I will stop sharing and then I will. So, Michael Tsunami asks, I typically have to use molecular dynamics engines like GROMACS, which are clunky to use any WL here to compute ligand protein docking, support for plan 15 plus? This is a great question. We do have these in like as potential plans, like docking and so on. This does require like a lot of design thought, and also MD simulations are computation intensive, but we are always thinking about how this can be incorporated as future functionalities. So yeah, stay tuned for that. Um, so let's see Q&A. Is there a built-in way to call AlphaFold 2 or 3 APIs within WL? So AlphaFold 2 or 3 APIs, no, not within WL. They have issues with licensing, honestly, and yeah. So the licensing seems fine for educational institutions, but it's rather restrictive for non-profit. So no kind of APIs for AlphaFold 2 or 3 for within the language, but it'd be great to have that kind of model in the future sometimes with API. Yeah. I'm doing vaccine target discovery. What WL can do? Can WL do delta G minimization? I need to check. I need to look at it. I need to think about it. I'm not sure if something can do it. I will ask the chemistry team and try to get back to you on this. Other questions. I typically have to use MD in this like Glomax, Amber or LAMPS, all in C++. Very tricky to compile on Mac. Any WL help here? Not at the moment, but we'll keep this in mind actually. So this is interesting direction for sure. Any plans of connecting to virtual reality? At this moment, we have not thought about it. So this is another great suggestion. So I will, yeah, keep that in mind. Thanks for this outstanding job. And yeah, thank you for coming. Thank you so much for your time. Yeah, I think, yeah, that's all from me. Maybe we can wait for a minute if there are more questions rolling in, or else and we can, yeah, stop this session. And yeah, I have copied my email in the chat. So if you have any questions in the future, feel free to, yeah, just email me, reach out. Okay. Thank you again for your time. It was great to talk about biomolecules, and we'll see you in next year's WTC.